Okay, let's start. Okay. I'll just fix this. Okay. Today we'll finish the panel data models. We'll go over the comparison of random effects and fixed effects estimation. Then we'll move on um, to binary choice models. Okay. Did you get already the handout for binary choice models? Okay, I'll just upload it. Mm. Mhm. Okay, I'll upload it. Mhm. Okay, okay, I'll share screen. Mhm. So, okay, so we've gone over we have been doing panel data models, and the basic models are the fixed effects, the random effects model, and the fixed effects models. Then we look at the estimation procedures. Um, we had pulled OLS, random effects estimation, fixed effects estimation, and we also went over LSDV, least squares dummy variable approach, and the first difference approach. Okay. Then I think I ended last time with incorporating time fixed effects, which can be quite important since you have time series data. Okay. Okay, let's go to fixed effects versus random effects estimation. Okay. Okay. Um, okay. Now going back to time fixed effects, note that here we do not have a subscript I, so we're assuming that this delta sub t affects individuals, um, the individual or the cross section unit i's in the same way. Okay. 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 And if you incorporate this, you need to have dummy variables. Okay. So this is different from the unobserved effect C sub I and the idiosyncratic error U sub IT. So delta sub T is the variable, the dummies would be observable. Okay. Let's move on to a comparison of random effects and fixed effects estimation. Okay. The random effects model, which is more restrictive because we have the assumption that the idiosyncratic errors are uncorrelated with the explanatory variables. Okay. No, sorry. We have the assumption that the that the unobserved or the individual specific effect is uncorrelated with the um, observed explanatory variables. Okay, the random effects model can be consistently estimated by both the random effects estimator and the fixed effects estimator. Okay, if we can be sure that the individual specific effect really is an unrelated effect, that is the first assumption for random effects models hold, then we would prefer the RE estimator. Why would we prefer the RE estimator? In this case, both the fixed effects and the random effects estimators are consistent. However, the fixed effects estimator is inefficient. Okay. This usually tested by the Durbin-Wu-Hausman test. We'll go through the Hausman test. However, the Hausman test is only valid under homoscedasticity and cannot include time fixed effects. Okay. Okay. That's why we will have another test, the auxiliary regression, um, to test for the unrelatedness assumption. Okay. If there is correlation between the individual specific effect and the regressors, then it is the fixed effects that is consistent and random effects is inconsistent. Okay. So the choice between RE, random effects, and FE, fixed effects, is primarily determined whether the individual specific effects, C sub I, are uncorrelated or correlated with the explanatory variables or the regressors. Okay. Let's go through the Hausman test. This is quite a popular test. Okay. What is the null hypothesis under the Hausman test? The null hypothesis is that the random effects model is the preferred model. So under the null hypothesis, C sub I, the unobserved effect or the individual specific effect is uncorrelated with the regressors. And the alternative is that you have fixed effects. The Hausman test basically tests whether the errors are correlated with the regressors. The null hypothesis is they are not. Okay. Under the null hypothesis of no correlation, that is, if the null hypothesis is true, there should be no difference between the estimators. Note that in the test of hypothesis, your test statistics are developed under the assumption that the null hypothesis holds. If the null hypothesis holds, then you have a test statistic, and under the null hypothesis, it would have some distribution. The test statistic would have some distribution. Okay. To carry out the Hausman test, you look at the difference between the fixed effects um, estimates and the random effects estimates, and its covariance is calculated. Okay. Um, Generally, when we do tests of hypotheses, we need the covariance of the estimators or some function of the estimators. Okay. Look though here, note that under the fixed effects, we are just able to estimate um, the coefficients of the time varying regressors. Okay, so that in fixed effects. Okay, so in fixed effects, um, we just estimated this. Okay, this is the fixed effects estimator. However, for the random effects, we estimated this. Okay, so for the random estimators, we're just getting this subset of coefficient estimates. Okay. Okay. The covariance of an efficient estimator with its difference from an inefficient estimator should be 0. Okay. Under the null hypothesis, that is zero correlation between C sub I and the X sub i's. The wild test statistic defined here would have a chi-square distribution with k degrees of freedom. Okay. Note that the dimension of this beta hat is k. So look at this formula. You have the difference transpose um, times the inverse of the difference of the asymptotic covariance matrices times again the difference. So this is chi-square. So you are really summing k standard normal, squared standard normal random variables. If W is significant, then we should not use the random effects estimator. Okay, so that is like in theta, you would get a line where you have the probability is greater than chi-square. If this is less than 0.05, our unassumed level of significance, therefore you would reject the null hypothesis and use the fixed effects estimator. Okay. To implement the Hausman test, you would run fixed effects estimation and save the estimates, run um, random effects and save the estimates. And you would also need to get these covariance matrices. Okay. Okay, so that's the Hausman test. But as earlier mentioned, the Hausman test is only valid under homoscedasticity and cannot include time fixed effects. Okay, time fixed effects being this. Okay, so The Hosman test can also have very restrictive assumptions. Okay, okay, another test um, you can use, and basically for choosing between random effects or fixed effects estimation, we're testing whether C sub I is uncorrelated with the time varying regressors. Okay, or that is RE1. Okay. This assumption, RE1, is better tested by running an auxiliary regression. Um, you do this by OLS. Okay. So estimate this by OLS. Okay. Um, okay. So note that okay, we have observations y sub it, x sub it, and c sub it. So this is the independent variable. These are the time varying regressors. These are the um, time invariant regressors which are observable. Now we can incorporate time fixed effects. Then we have this x sub I, x bar sub it, which is this. And this is just the time average of um, the ith regressor here. Okay. Okay, so you have to get this for all time varying regressors. Include the time fixed effects if they are included in the RE and FE estimation. Okay. Then how do you do this test? Then you run the OLS, then post estimation, you test whether the coefficient here is equal to 0. Okay. To do this test, because we want to allow for heteroscedasticity and serial correlation, use cluster robust standard errors. Okay. Note that RE1 is an extremely strong assumption, and the FE estimator is almost always much more convincing than the RE estimator. Okay. However, not rejecting RE1 does not mean accepting it. Okay. Interest in the effect of the time invariant variable is not a sufficient reason to use the RE estimator. Okay. Um, so some might be interested in note that the fixed the random effects estimator, the fixed effects estimator will only estimate beta, okay, but not alpha and gamma, okay. Now, is not sufficient reason that you want to estimate, let's say, gamma, the coefficient of the time invariant regressors, okay. Gamma is the um, coefficient vector associated with C sub I. So C sub I, for example, for an individual person, this can be, for example, gender. So for that person, gender remains the same across all time periods. Okay. But if you want to look at the effect, the partial effect of gender, then you cannot do that using fixed effects. Okay. But it's not sufficient reason for you to do random effects um, because you would mess up the estimator also if C sub I is actually correlated with um, these regressors. Okay. Okay, so that's the comparison of random effects and fixed effects. Okay. So for Stata, these are just some commands you might encounter XDREG, FE for fixed effects, RE for random effects, VCE for the robust standard errors, Husman for the Husman test. Auxiliary regression, you have to write out the commands for the auxiliary regression. Okay? So you have to do OLS using the regress command. You have to generate these variables and so on. Pull the OLS, which is just regress. Then you should also know how to do least squares, dummy variable. If you have many individuals or cross-section units, for the printout, you might want to suppress the printing out of the coefficients, and you can use this command areg. You should also know how to implement first difference estimation. Okay, so that's it um, for panel data models. Okay. Do you have any questions there?
No, ma'am.
Let's move on to um, binary response models. Again, we'll just go over the basic models, which are uh, probit and tobit. Um, okay, so I have uploaded to the chat box this file. Okay, we'll have a short introduction of the binary response models, its major features, and then we look at the specific economic models, the probit and the logit, and then we'll have an alternative interpretation of the probit and logit in the context of latent variable models, which are quite helpful. These latent variable models are quite helpful in our limited dependent variable models. Then we'll look at the interpretation of estimators, and then we'll go to estimation using maximum likelihood and OLS. Okay. Okay. Um, okay. So this is really the basic discrete choice model, where we have a binary response in the left-hand side. Okay. Many dependent variables of interest in economics can take only two values, usually denoted by 0 and 1. The values 1 and 0 can be assigned arbitrarily. Okay, it just makes simpler the analysis in terms of notation if we use 0 and 1. You can use, let's say, -5 and +3 um, for the binary variable. You would still get the same results. Of course, you would then have to um, modify your interpretation. Okay. Okay, so for these variables where we just have two choices on the left-hand side and they are discrete, such variables are called dummy variables or dichotomous variables. Okay. An example would be, for example, would would be if on the left hand side of the equation we have the labor market status of a person. Okay, the variable takes the value 1 if a person is employed and 0 if he is unemployed. Okay, now the expected value of a dichotomous variable y sub I belonging to 0 1 well, it's either 0 or 1, is the probability that it takes the value 1. Okay. Okay, for this, you have to review discrete random variables, Bernoulli random variables, and moments of discrete random variables. Um, I guess you had this in 241. Did you have this in 241?
231, ma'am.
231.
No. Uh, 231, sorry.
Yes, ma'am.
You had this. Okay, so just do that. Okay. Or another way of looking at y sub I is it is a Bernoulli random variable. But Bernoulli random variable is a discrete random variable. Okay. And then you should know how to get the moments of discrete random variable. So for discrete random variables, you use summation signs in term rather than integral, um, the integral operator. Okay. So what is the expected value of y sub I? Okay, so this is just well, mm, well, if you have a random variable y, the expected value of y is just the sum of y sub I times the probability of y sub I over all possible values of y. Okay. Okay, so you just use this. So the expected of value of y sub I, this is a specific observation, is 0. So it's either 0 or 1. You multiply 0 by the probability that y sub I is equal to 0. 1 times the probability that y sub I is equal to 1. Okay. However, the first term would be 0. So you get the probability that y sub I is equal to 1. Okay. That's why we have here the expected value of y sub I is the probability that it takes the value y sub I is equal to 1. Okay. Then let's consider the linear regression model. Y sub I is equal to x sub I transpose beta plus v sub I, where the expected value of v sub I given x sub I is equal to 0. So we're assuming here that the x sub i's are exogenous. Okay, and then just to make clear the notation for the disturbance term, we have v sub I instead of u sub I. We will be using u sub I later. Okay, so this model is called the linear probability model, where y sub I is either 0 or 1. Okay, the limitations of the linear probability model are as follows. The expected value of y sub I given x sub I. So if you get the conditional expectation of this, that is equal to x sub I transpose beta. Okay, so it's the expected value of the right-hand side. So the expected value of this given x sub I is fixed, beta is also fixed. So you have x sub I transpose beta plus the expected value of v sub I given x sub I, but that is 0. Okay, so we're left with the term x sub I transpose beta. Okay, now this note that your observed values are 0 and 1, but the expected value can lie if you look at this x sub I transpose beta. This can lie outside 0, 1. And if it's outside the interval 0, 1, then it does not represent a probability. Okay, so if this x sub I transpose beta is outside the interval 0, 1, you don't have a probability. Okay, and moreover, the error term is heteroscedastic. Okay, so this V sub I is heteroscedastic. So get the variance of V sub I given X sub I, the conditional variance of X sub I, and you should get X sub I transpose beta times 1 minus X sub I transpose beta. And note that this depends on X sub I. Okay, so the variance here is not, the V sub I is not homoscedastic. Okay. Therefore, if you use OLS on this model, then you would be violating the Gauss-Markov theorem. So for this, I want you to verify that you have, I want you to verify this. Okay. Okay, so you have to use the variance formula for discrete random variables. Okay. Um, and you have to use the information, if phi sub I is equal to 0, what is V sub I? If y sub I is equal to 0, then V sub I is minus X sub I transpose beta. And then y sub I is equal to 1, then V sub I is equal to 1 minus X sub I transpose beta. Okay. Okay, so that's the, so we have laid out the framework for the linear probability model. It's basically the linear regression model, um, where the dependent variable is either 0 or 1. Okay. Okay, now let's look at the two binary response models, the probit and the logic. Okay, the binary response models directly describe the response probabilities. The response probability is this. That is what we mean by the response probabilities. When we go to the other limited dependent variables models, you would always encounter the term response probabilities. So in this model, we're looking at, for the response probability, uh, the probability that y sub I is equal to 1. Okay. Okay, so now let's consider a sample of n observations. We're doing random sampling from the same population. So each of observations, the observations then are independently and identically distributed. Okay, we're sampling from the same population. So we have n observations. So our index for each cross-section unit would be going from 1 to down to n. Okay. So we would have data on the dependent dummy variable y sub I and a k plus one dimensional vector x sub I transpose of explanatory variables, including a constant term. So going back to our model, um, we would have sample data on y sub I and x sub I. Okay. So this beta is a k plus one vector of parameters, unknown parameters, which include the constant term. Okay. So x sub I here would include 1 for the constant term. Okay. Okay. The probability that the dependent variable takes a value 1 is modeled as follows. The probability that y is equal to 1 given x sub I is uppercase f, a function of c sub I, which is equal to f of x sub I transpose beta. Here, c sub I we define to be equal to x sub I transpose beta. Okay, so that's just a matter of notation. Okay, so here beta is a k plus one dimensional column vector of parameters. So this c sub I is a single linear index. Okay, the function f maps the single index c sub I into 0, 1 and satisfies in general f of minus infinity is 0, f of positive infinity is equal to 1. The partial of f with respect to z is greater than 0, which means f is a positively monotonic function of z. When z increases, f also increases. Okay, so these equations hold for both the probit and the logit. Okay, so that's the common framework for um, the probit and the logit model. Okay, so how do we get the probit model? The probit model assumes that the transformation function f is the cumulative distribution function of the standard normal distribution. Note that these properties, these properties are satisfied by the CDF, right? For a CDF, its value at negative infinity is 0, its value at positive infinity is 1, and the partial of f with respect to z is greater than 0. It's positively uh, monotonic. Well, not always. Sometimes you can have flats in f, um, but then in the probit and the logit model, we would have um, this being satisfied. Okay. Okay. So the response probabilities for the probit would then be okay. So we have the probability that y sub I is equal to 1 given x sub I. That is we have it here. It is f of c sub I or f at evaluated at x sub I transpose beta. Okay. So if we let f to be the CDF of the standard normal distribution, then we have phi, uppercase phi, as the CDF of the standard normal distribution evaluated at x sub I transpose beta. And what is this CDF? The CDF is the integral from minus infinity to x sub I transpose beta of the standard normal density function. Okay, so lowercase phi is the probability density function. Then we're integrating with respect to t. Okay, writing out this um, standard normal density function, then its mean is zero, its variance is sigma square. So this gives us, okay, so this is our phi of t. Okay, so we have 1 over square root of 2 pi e to the minus 1 half t square. Okay. How about for the logit model? The function, the transformation function f is the logistic function. Okay, the response probabilities are then given by this. Okay, so this is the CDF evaluated at x sub I transpose beta. Okay, so that is this. Then if you divide the numerator and denominator by e to the x sub I transpose beta, then you get 1 divided by 1 plus e to the minus x sub I transpose beta. Okay. The probit and logit models are almost are almost identical, and the choice of the model is usually arbitrary. However, you can try this out in Stata. You estimate the linear probability model using either both using probit and logit and compare the parameter estimates. Okay. However, the parameters beta of the two models are scaled differently. Multiplying the parameters in the probit model by 1.6 yield approximately the same as the logit estimates. Okay. Um, okay. Where did they get this 1.6? The factor 1.6 is derived from equating the first derivative of f in the probit model. Okay. So get the derivative of this with respect to x with the one in the rescaled logit model. Okay. Then rescale this 1.6, no, divided by 1.6. Then get the derivative with respect to x. Okay. This is appropriate scaling for the marginal effect of the average type. An alternative approach is to create the standard deviation of the distribution for which f is the CDF. For the probit model, the standard deviation is 1. Note that we have the standard normal distribution and the variance is 1, therefore the standard deviation is 1. And for the logit model, you have pi over square root of 3, which is approximately 1.81. Okay, so that's the basic binary response models. We define the response probabilities. They are probabilities, so you want the numbers we get for these probabilities to be between 0 and 1. Therefore, we use the CDF. Okay, so for the probit, we use the standard normal distribution. For the logit, we use the logistic function. Now let's have an alternative interpretation of the probit and logit model in the context of latent variable models. Okay, latent variable models are also often used in limited dependent variable models, okay, or uh, and other areas in advanced econometrics. Okay, is a latent variable because the variable cannot be observed, so you cannot measure it. The latent variable model provides an alternative interpretation that gives rise to the probit and logic models. Consider a latent variable, y sub I star, which is not observed by the researcher and linearly depends on x sub I. Okay, so y sub I star linearly depends on x sub I. Then here we have u sub I with the usual exogeneity assumption. The expected value of u sub I given x sub I is equal to 0. So we're not worrying about endogeneity here. The problem we're trying to address is this. Well, in the latent variable model, this is unobserved. Okay. The latent variable, however, what we observe would be 0, 1 variables. The latent variable y sub I star can be interpreted as the utility difference between choosing y sub I is equal to 1 and y sub I is equal to 0. But we know that utility, the value of that utility, um, we cannot observe. In fact, we have the ordinality characteristic of utility functions. Okay. This then is called a random utility model when we interpret y sub I as the utility difference between choosing y sub I is equal to 1 and y sub I is equal to 0. Okay. Only the choice y sub I is observed by the researcher and it takes on values 1 or 0. Okay. An individual chooses y sub I is equal to 1 if the latent variable is positive, so y sub I star is greater than 0. Otherwise, she chooses 0. That is the case where y sub I star is less than or equal to 0. Okay. So we just laid out the latent variable model. Okay. So y sub I star is unobservable, but assumed to depend linearly on x sub I. But what we observe is y sub I, a Bernoulli random variable that takes on the values 1 or 0. Okay, so where does the probit model come in? So here note that normality assumption comes in through the assumption on the disturbance term. Okay. Furthermore, assume that the individual observation x sub I, y sub I are identically and independently distributed. So that's satisfied if you have random sampling from the same population, that the explanatory variables are exogenous. Okay, that satisfies this. And that the error term is normally distributed and homoscedastic. So we have this assumption. Okay. So we have two strong assumptions here. The variance sigma square is constant across the use of i's, and also the disturbances are normally distributed. So we have error, the error term, the conditional error term is normally distributed and homoscedastic. Now let's derive the response probability. Okay, the response probability is the probability that y sub y is equal to 1 given x sub I. Okay. Um, in the context of the example mentioned earlier, where y sub I is labor status of the individual. So this is the probability that a person is employed given the x sub i's. Okay. Um, so for here, uh, okay, so we have this. What is the probability that y sub I is equal to 0 given x sub I? What is the probability that y sub I is equal to 0 given x sub I? In the example, what is the probability that the person is unemployed given x sub I? Then this is just 1 minus the probability that y sub I is equal to 1 given x sub I. Because y sub I can only take on the values 0 or 1. Okay. Okay, so we have the probability that y sub I is equal to 1 given x sub I. And looking at this, the probability that y sub I is equal to 1 is the same as the probability that y sub I star is greater than 0. Okay. So we have the probability that y sub I star is greater than 0 given x sub I. Okay. But what is y sub I star? Y sub I star is defined here. That is x sub I transpose beta plus u sub I. Okay. So y sub I star is x sub I transpose beta plus u sub I. Okay. Then we can just manipulate this event. So you would have u sub I is greater than minus x sub I transpose beta. Okay. So we wanted to isolate u sub I because we have information on the distribution of the u sub i's. Okay. Okay. So if you look at this, the probability that u sub I is greater than minus x sub I transpose beta, conditional on x sub I, is equal to 1 minus the complement of this. So that's the probability that u sub I is less than or equal to minus x sub I transpose beta given x sub I. Okay. But we're working with standard normal with we want to have a standard normal um, variables. So let's subtract. So we subtract 0 and divide by sigma both sides of the inequality. So we get this. Okay, so this is 1 minus. So if you look at this expression, that is just the CDF evaluated at minus X transpose beta over sigma. Okay. But because of the symmetry of the standard normal distribution, you get this is equal to phi of X sub I transpose beta over sigma. Be sure you can work this out. Okay. Uh, so verify this. Just as an exercise on the stand on the normal distribution. Okay. Okay, so you get the Probit model when sigma square is set to unity. Okay, so note that if sigma square is set to unity, sigma is also equal to 1. Therefore, you get the probability that y sub I is equal to 1 given x sub I is the CDF evaluated at x sub I transpose beta, okay, which we have earlier, okay, we had it here, we had it here, okay. So if you set sigma is equal to 1, then we get back the probit model. Okay. Note that beta k and sigma are not separately identified as only the ratio beta over sigma can be estimated. Okay. The logit model can be analogously derived using the latent variable approach. Then you just change the assumption on the distribution of the disturbances. Okay, so you would be changing this assumption for the logistic distribution, for the logit model. Now let's look at the interpretation of the parameters. Okay, let's look at the marginal effects, the predictions, and the predictions. Okay, so you would get these using post estimation commands after you have run probit or logic. Okay, so different from the linear regression model, the parameter beta cannot directly be interpreted as marginal effects on the dependent variable y sub I. Okay. Okay. So for example, for the probit, you cannot interpret beta as the marginal effect of x sub I on y sub I. But this gives us the relationship between the response probability and x sub I transpose beta. Okay. In general, we are interested in the marginal effect of a change in x sub ik on the expected value of the observed variable y sub I. Okay. So we're interested in the effect of a change in x sub ik, one of the regressors, on the expected value of y sub I or the mean value of y sub I. Okay. So note that this expected value can be between 0 and 1. Okay. Okay. But what is the expected value of y sub I given x sub I? We have taken that in the first. Okay. So here, if you have the conditional expectation, the expected value of y sub I given x sub I, then that is the probability of y sub I equal to 1 given x sub I. Okay. So we lay that out in the introduction. Okay. So what we do then is using the probit model, we get the partial derivative of that probability with respect to x sub I. But for the probit model, what is this probability? The probability that y is equal to 1 given x sub I is this, okay? Or uh, setting sigma is equal to 1, or it is this, okay? So you have to get the derivative of this with respect to x sub I k. You have to get the derivative of that. Okay, so what would be that derivative? Okay, so you have to get the derivative of this with respect to x sub I k. Okay, so you have to use the chain rule. So get first the derivative of phi with respect to x sub I transpose beta, or you can let this be z, the partial of the CDF with respect to z, the partial of z with respect to x sub I k. Okay, the derivative of the CDF with respect to z, c sub I would be equal to the density function evaluated at x sub I transpose beta. Then you get the derivative of this with respect to x sub I k. Then you would be picking out beta k. Okay. Note that this is for an individual, so you can get this for I going from 1 to n. Okay. And these values can differ from individual to individual. Now for the logit, okay, so we have the same steps, but then you get the derivative of, okay, so for the logit, this is the probability that y is equal to 1 given x sub I. Therefore, you have to get the partial of that with respect to x sub I k. So get the derivative of this, okay? Okay, so note that this is note that this is a quotient. Okay, um, so suppose you want to get the partial of that with respect to let's say some variable um, some variable x. Okay, so you can use the formula for either a quotient. So what is the formula? So you have v squared v du minus u dv, right? Or you can use um, you can express that as the partial of uv inverse. So that would be u, the derivative of v inverse over dx plus v inverse times the derivative of u with respect to x. Either way, you should get the same answer. Okay, so note that you have a square here in the denominator. And using the chain rule, if you get the partial of x sub I transpose beta with respect to x sub I k is beta k. Okay, so these are the marginal effects. And note that you have the subscript y I for y. Therefore, these expected values can differ from cross-section unit to cross-section unit. Okay. Note that the marginal effect depends on the values of all explanatory variables. Hmm. Um, this shouldn't be here. Therefore, any individual has a different marginal effect. There are several ways to summarize and report the information in the model. Okay, you should be able to do both. A first possibility is to present the marginal effects for the mean type. That is, x sub I is equal to x sub I bar. That is your finding the marginal effect at the mean. Okay, or you can choose the median type or some interesting extreme types. Okay. The second approach is to calculate the marginal effects for all observations in the sample and report the mean of the effects. So solve for this for each observation and get the average. Okay. So these are three different ways of summarizing um, the estimates you obtain. Okay. Another use of the estimated model is in predictions. Okay. So what would be the estimated probability that y is equal to 1 given x sub I? Okay, this is the response probability. Then it's the same as what we had earlier. Okay, so we had this for the probit. So you just substitute beta hat for beta, and therefore you would get an estimate p hat. Okay. The same thing for the logit, just substitute beta hat, then you get p hat. Okay, so these are the predicted values of the left-hand side variables. No, not the predicted value of the left-hand side variable, but the predicted value of the response probabilities. Okay, so note that you are not predicting what y sub I would be, but what is the um, response probability. Okay, so here, for example, you are looking at the probability that a person would be employed. Okay, okay. For a discrete explanatory variable, it is more accurate to report the effect of a discrete change, delta sub ik. The discrete effect of a dummy variable x sub ik changing from 0 to 1 is estimated as follows. So you get the predicted value when x sub ik is equal to 1. Subtract the predicted value when x sub ik is equal to 0. Of course, you have to set the other regressors to some other values. Okay. So this effect of the dummy variable on the response probabilities depends on the values of all other explanatory variables x sub I L, L not equal to K. Okay, so note for if you have a dummy, if x sub I K is a dummy variable, it does not make sense to have the marginal effect. You cannot have the marginal effect. You cannot have this marginal effect because x sub ik goes from 0 to 1. So you have to estimate it using this. Using this. Sorry. Predictions can also be aggregated to, for example, the predicted number of observations with y sub I is equal to 1. Okay. So suppose you have a sample of 1,000, you would like to have what is the predicted number of persons that would be employed out of that 1,000. Okay. So that is the predicted number of observations with y sub I is equal to 1. Okay. There are two prediction methods for this aggregate. So one is if the predicted probability is greater than zero point 0.5, then assume y sub I hat is equal to 1. Therefore, your predicted number of observations would just be the sum of y sub I hat over all i's. Okay, note that this y sub I hat would be 0 or 1. So summing the ones would give you the number of observations with y sub I is equal to 1. Okay. Or an alternative is sum the predicted choice probabilities. Okay. The two measures can be contrasted to actual numbers. Method 1 also allows for comparison of actual and predicted outcomes for any observation. Okay. It is also often interesting to report and contrast predicted numbers for certain types of individuals. Okay. Okay. I think I better stop here because I want to go more slowly with the maximum likelihood estimation. Okay. Um, okay. So after the reading break, then we'll restart on this topic, estimation using maximum likelihood, and what are the implications if you do the estimation with OLS. Okay. And then I'll move on to other limited dependent variable models. Any questions? Have you
Mm,
gotten your problem sets 3 and 4?
Yes po.
So you have to work on that. Okay. Maybe for okay, okay, just focus on that first. Okay. Any questions? Okay. So just rework through the notes, and be sure you can follow it step by step. Okay. Then it will become easier for you doing the problem sets. Okay. At least you would have a feel of what's going on. It's not just doing data and groping what the numbers mean. Okay. Okay. Any questions? None. Okay. So we'll meet on Thursday next week. Okay.
Okay po, ma'am. Thank you po.
So good
Thank you
luck.
po.
You have an exam today?
Yes po.
Yes po.
Okay, so I'll let you go. Have a
Thank
good
you
day.
po, ma'am.
Okay. I would
Bye
have
po.
left you. Okay. So good luck in your exam later.
Thank you po, ma'am.
Sige. Bye. Hi, Charles.
Hello, ma'am.
Oo.